Okay, we are now recording. We're on page 80, chapter 2, section 2.4, example 6. Okay, and I think I'll go to this slide. And no, sorry, that's what. From current slide. Okay. Oh, and it might help to turn on the projector. All right, let me mark roll 2. Cameron's here. That took a while. Hopefully Ashley and or Yvonne may show up, but I kind of doubt it. Because they weren't here at the first class, so I doubt if they'll make this one. Okay, as soon as we will, in fact, I can go on and start writing on my thing. If a square matrix A row reduces to an upper triangular matrix U using only the row operation of adding a multiple of one row to another row below it, then it is relatively easy to find the LU factorization of matrix A. All you need to do is keep track of the individual row operations as shown in the following example. Okay, now notice this is saying if it's just adding a multiple of one row to another row. If you divide or multiply a row by something or swap rows, might be a little more difficult. Okay, so find the LU lower upper factorization of the matrix A. And for some reason, unless you did something too.
That's what it does.
What's that?
That's what I was talking about. It's not going to format to the projector. It's
Oh.
not going to make it stretch it or shift it over or anything.
Right.
So
But right now my screencast-o-matic thing's here. You can barely see it. Yeah. And this is up here, and it's not going to interfere. Right. Okay.
That's kind of what I did. I
Okay.
figured that'd be easier.
All right. So here is matrix A. One, negative 3, 0. 0, 1, 3. And 2, negative 10, 2.
Is it just me or is that seem dim?
I think the projector has just come on, so it probably is going to get a little bit lighter. But another thing is, I notice that every now and then this thing gets very dusty. That's not going to make it any brighter, but I just, when you said that, I looked this off. It's really dusty. But yeah, it does really look dim now.
Maybe turn on phase lights, make it easier to see.
Yeah. I don't think it's getting any brighter, is it? Either, is it? Is there?
That helps some.
Was there something that you did that would have changed that too?
I don't think there's anything I could have done to affect the brightness.
What's that?
I don't think there's anything I could have done to affect the brightness of
Yeah.
the projector.
Bizarre. But anyway, find the LU factorization of that. Okay. Well, so what we want to do is begin row reducing to get a which kind?
The upper triangle.
Upper triangular matrix. Okay. And what would we do? What would be one step to get that?
Negative 2, row 1 plus row 3.
Yeah, negative 2, row 1 plus row 2 is the new, row 3, I'm sorry, is the new row 3. Okay, so this would become, we're dealing with we're using the first row, so write it down, 1, negative 3, 0. Row 2 was fine, so we leave it alone, 0, 1, 3. And the new row 3 is, and that, by the way, is a 10, not a 14. Okay. What do you get?
0.
0.
Negative 4.
Okay. And 2. All right. What do we have to do now?
Do we not have to write the elementary matrix alongside of it?
Oh yes, we do. Sorry about that. We have to be keeping track of that too. And so I should have gone down, but here's the elementary matrix here. What did we do?
It was 1, 0, 0.
Yeah, 1, 0, 0 stayed the same.
0, 1, 0.
0, 1, 0 stayed the same.
Negative 2, 0, 1.
Okay. You do the same operation to the identity matrix, and that is exactly what you would have got. Okay? What you going to do next?
Let's see. We're going to get the negative 4 to be 0. So
Okay.
negative, or well, let's see, positive 4, row 2.
4, row 2.
Plus row 3.
Row 3. Okay.
And I do that, and then I
So
do
it's
the
1.
elementary matrix first.
Okay. Okay. Oh, did you say you're going to do elementary matrix first?
I figured you were going to go ahead.
Oh, okay. Yeah. Well, let's do it then. Okay.
0, 0, 0.
Okay.
That'd be 0, 4, 1 for the last row of the elementary matrix.
Right.
0, 4, 1.
All right.
And the bottom row of that one would be 0, 0, 14.
Okay. That would be, yeah, 14. All right. And it doesn't matter, that's not a 1. All you want is an upper triangular. You got it. So here's our U. Upper part of the loop. Okay.
Do we need to find the loop, the L part of the loop?
Right. Now, the reduced matrix U, the upper triangular that we have here, and here, by the way, is how we got it. Okay, we started with A, and we did the row reduction, but that was the same. This is, I think they called E1, didn't they? Yeah. And this is E2. Okay. So we multiplied on the left by E1 and then by E2. Okay. Now, we need to do something to get this back to A. Okay. Now, and this, by the way, is equal to our U. Right? To get back to A, we are first going to multiply by the inverse of E2, which is going to wipe that out. So then we'd have E1A is equal to E2 inverse times U. And then we would do multiply by E1 inverse, and that would give us A is equal to E1 inverse E2 inverse U. Well, therefore,
Flip some around. It flips some around.
Right.
2, 1 to 1, 2.
Exactly. And what this has to be then, and this isn't bad. Let's see if that makes it a little sharper, but it doesn't make it any brighter.
Brightness. There it is.
I've never
It's in the
found
menu.
one.
Brightness at negative 14. That might be the problem.
Let's do a 1.
I was saying how to actually see there. I don't think that's helping.
Okay. Try 0. See what you get.
maybe reset.
Yeah, try that.
Sure. Can you, let's see, maybe escape the PowerPoint and see what it looks like outside the PowerPoint? If it's just being the PowerPoint. If it's
Should I keep or discard?
you can go ahead and discard up.
Yeah.
It's still pretty dim.
Yeah. I don't know. I wonder if one of my bulbs.
If your bulb is going out.
Yeah. I don't know if this is an LED projector, but if it is, usually they have several different LEDs in there. And if one of them blue, then that might, or more than one blue. Or maybe turning it off and back on again. I don't know.
Yeah, that might work.
Let's try that.
It is significant.
Wonder if I need to let the fan run down or if you only turn it back on. Oh, I think I've got to let it run down because it won't turn on again until that quits flashing. But we are recording. Okay. Now let's see what happens. Okay. So what we had before, let me get this. Okay. We had I don't think yeah, we do need it. No, we don't. All we need is E1, inverse, and E2. So let's do E1, and that was 1, 0, 0, 0, 1, 0, 2, or was it negative 2? Negative 2, 0, 1, right? And E2 was 1, 0, 0, 0, 1, 0, 0, 4, 1. Okay. Now we need the inverse of each of these. E1 inverse. And remember, if all you're doing is changing, I think this comes out 1, 0, 0, 0, 1, 0. And this is now a 2, 0, 1 or negative 2, 0, 1.
Before it was negative 2.
Yeah. Yeah, I know, but the inverse of, going back to doing the inverse of an elementary matrix.
It'd be negative 1/2, or no?
No, it stays the same number but changes sign.
It's 2,
Yeah.
It's 2.
So it becomes 2, 0, 1, and E2 inverse becomes 1, 0, 0, 0, 1, 0, 0 minus 4, 1. Okay. Now, and we want to multiply those together in that order. So this will be 1, 0, 0, 0, 1, 0, 2, 0, 1. Let me clean that up just a little bit. Well, there we go. I can hardly, well, it acts like it takes, there it did. All right. All right, good. Okay. 2, 0, 1 times 1, 0, 0, 0, 1, 0, 0 minus 4, 1. Multiply those two together, and what size you get? 3 by 3. And
Pretty sure you get 1, 0, 0, 0, 1, 0.
okay,
And 2, negative 4, 1.
2, negative 4, 1. Okay? And guess what? That is a lower triangular, which we wanted it to be. It needs to be. So this is our L. Okay? We already had the U, which you'll have to remind me what that was.
This is 1, negative 3, 0.
U equal 1, negative 3, 0.
0, 1, 3.
0, 1, 3, and 0, 0, 14, was it?
Right.
Okay. All right. So, I think that's all we had to do, wasn't it? Find the LU factorization. We did. There's L, there's U.
Or do we need to multiply them together?
You can to check it,
And it would give us A.
and it should give us A. But you have to multiply LU. So that would be, let me write my U here. 1, negative 3, 0. 0, 1, 3. I'm sorry, I'm not writing well. What's happening is my pen is lagging so badly that I'm writing too fast and I'm not getting it where it needs to be. Okay, so let's see about multiplying those two together and see if we indeed get it. Well, that gives us a 1, right? And which one you want to do next? Below it?
1, 0, 2 going downwards. Like that.
1, 0, 2.
Yeah.
Oh yeah, right. Okay. You're going on and doing it all, which is I didn't write down A, so we're guessing now. Okay.
Negative 3, 1. And that's where I was stopped.
Negative 3 what?
1. Alright, so the bottom row would be
Oh, that's where you were. Okay.
negative 6 minus 4, which is negative 10.
Yep.
Alright, and then the last row would be 0, 3, 0, negative 12, would be 2.
Second?
Be 2.
2. Okay. Got it.
And
I believe that's what A was. Yeah.
Was that
That was exactly A. Now, you didn't have to do that, but that confirmed confirm what we had. Okay. Here the LU is a product of inverses of the interview. Okay. We did that. Once you obtain the LU factorization of a matrix A, you can then solve the system of n linear equations in n variables. I don't guess I need this anymore, so I'm going to go to a clean page. I sure hope I don't. I'd hate to have to write all that again. Okay. So here's your A, X equal B. All right. Here are the steps to solve that. First, come up with a new vector y, which is equal to ux. Okay? Pretty straightforward once you have that u done. Okay, and what you do now is solve that, and you do ly is equal to b. Okay? Solve that for y. Okay?
So vector B divided by L.
No, you don't divide by, multiply by the inverse of. Okay. But you could do that, or you could. This is a lower triangle matrix. I want to do row reductions and get y. Yeah. No. Let's see. That's not right. Yeah. Well, I think having it in front of us will do it better. And then this is step 1. 2 parts of step 1. Then solve ux equal y for x. This is for y, and this is for x. Okay? Now, then multiply by ax, which you've solved here. That's equal to lux, because that is indeed what it is, and that's equal to b. Okay. Now, that second step, that's this one, is just back substitution because the matrix U is upper triangular, and the first step is similar except that it starts at the top of the matrix because L is lower triangular. For this reason, the first step is often called forward substitution. Blah, blah, blah. Okay, let's actually do this with a matrix and see how this works. And I think I'll go on, rather than running into problems like we did before, we will erase all this and then start over. So here's our linear system. x1 minus 3x2 is equal to negative 5. x2 plus 3x3 is equal to negative 1. Liking their negatives here, aren't they? 2x1 minus 10x2 plus 2x3 is equal to negative 20. Okay. Now, time out. What do you notice about this? What would be your first step?
Matrix.
Yeah, and what would be your matrix?
1, negative 3, 0, 0, 1, 3, and 2, negative 1, 2.
2, negative 10.
Oh, negative 10, sorry.
Okay.
0,
Look familiar?
yeah, it's matrix A. And then
Huh?
It's matrix A, so I can go
Yeah, that's the matrix A we had before. Exactly. Okay? So we've already done the LU factorization. Right?
Right.
Okay? So that is AX equal B, and this is your B here. Okay? You could write that as LU. Now let me write, the lower was, if I'm not mistaken, 1, 0, 0, 0, 1, 0, 2, negative 4, 1. Lower. The upper was 1, 3. I don't remember.
I can tell it to you.
I can look on the previous page. Okay. Oh wait, I'm looking at the wrong thing. I guess they didn't write them out here, did they? Okay, tell me. 1, negative 3, I was thinking that was it. 0, 0, no, yeah. 0, 1, 3?
Yeah, and then 0, 0, 14.
0, 0, 14. Okay. And that's equal to, or times x is equal to b. Yeah. negative 5, negative 1, negative 20. If I copied it right. Yes. Okay. Now, the first step we had, let y equal ux. Now, this, remember, is L, this is u, and this is x. Okay? So y is equal to ux. That's 1, negative 3, 0, 0, 1, 3, 0, 0, 14 times x1, x2, x3. Okay, slow on the pen, but got it. Okay. All right. Now,
do we need to multiply that by the negative 5, negative 1, negative 20, or do we need to
right.
solve for x1, x2?
Okay. Now, so that's your y. Multiply that. The next step is Ly is equal to b. Okay? Well, your lower triangular, okay, comes out okay. So that's your y. Your lower triangular is basically this thing times that thing is equal to b. Okay, well, that should be a little b, sorry. Not that it matters any, but trying to be a little more consistent. All right. Okay. Now, and you could write this as y1, y2, y3. That would be what y is. Okay. Now, so basically, I don't know if this is helpful or not, but this shows you, and starting from the bottom, 14x3 is equal to y3, right? So x3, let's see, do we want that? Oh, wait, okay, let's leave that alone for now. For the moment, we won't do that. Yuck! All right, took it that time. Okay. Okay. Now, let's just write down this. Our lower triangular matrix is this one, which is 1, 0, 0, 0, 1, 0. All right. I love it. Okay. 2, negative 4, 1. And then this would be our y1, y2, y3. Okay. And that's equal to our -5, -1, -20. All right. Now, where we're starting here is that 1 times y1 is equal to -5, right? You see that? y1 is equal to -5. Okay? And I think we can also see that y2 is equal to -1. Okay? And then that negative, or let's just call this -10 plus 4 plus y3 is equal to -20. Wait, okay, now, so y3 is equal to, yeah, that would be a -6, add that, yeah, -14. Okay. Now, that tells us y3 is equal to 14 times x3, so that means x3 must equal to -1. Do you see that?
Say that again.
Okay. y3 is equal to -14. Okay? And this tells us that 0 plus 0, 14x3 is equal to y3. So 14x3 is equal to -14. Divide by 14 and you get x3 is equal to -1. Right? Okay? And then back substitution, that way, that was what they call forward substitution. Back substitution here then gives us that x2 plus 3, yeah, minus 3 is equal to -1. Okay? So x2 is equal to 2, right? And then the last one is x1 minus 6, right? Is that right? Yeah, minus 6 is equal to -5, and that tells us that x1 is equal to 1, if it'll write. Okay, so here we have our solution. Okay. Now, you see, you just set this up and let it sit. Then you go through and solve that for y using forward substitution. Then you use those values to come back here, back substitution, and you go this way. Okay? A whole lot more work, okay, than doing simple row reduction of an augmented matrix. But the advantage is if you had different values here, then once you got this thing set up, it's really easy. If you had different v's here, just put in a new v, and it goes just as fast as here. But you can't do that with row reduction because you have to go back and go through the whole process again. So this technique works if you have a given matrix here, a given part here, and you're wanting to test different values here, output values or whatever you want to call those. And in some models, that's exactly what you do. You want to see, well, what would I need if I wanted to do this? Well, what would I need if I wanted this? And what would I need if this is your, say, your manufacturing constraint, that your equipment, your personnel, your resources is all like this, come up with equations here, and this is your output here that you're getting from those things. then, well, in order to get that output, what am I going to need to put in, to here? It went. I guess it was in the process of going.
That's frightening.
Yeah, I've never had one blow like that. I've had them not come on, but I've never had one blow. I guess the dullness had something to do with that. There was a little bit of smoke there.
Yeah, it was like a puff.
Yeah. And I guess it's already shutting down. It's just cooling off, so I'll let it cool off. So what do we do? How much time we got?
Good 40 minutes.
40 minutes. Les, you want to go next door? Because I don't think they want to there.
Do they have a projector over there?
Yeah, there's one ceiling mounted. I'm supposed to have one in here, but they've never put it up.
Maybe it's about time.
Huh?
I said maybe it's time.
Yeah.
Are you sure that's turning on?
Yeah, that's what happens when you do this, but that probably got quite hot, so it's going to have to cool off for a while, I think. Okay. So what I'll do is disconnect here.
I would pause integrity.
Huh?
I would pause integrity.
Yeah, let me go. Fault, it's not integrity anymore. Now we're recording again, but an interesting thing is, now it's chopped off the bottom of my screen. Let's see. Huh. Strange. You know, where I wrote all those things down in there. And it looks like it chopped off a little on the edge over there, too.
I don't know. Can you still write?
Yeah, let's see. The good news is we probably were pretty close to finishing that problem anyway. I remember X3 was -1, wasn't it? Yeah. X2 was now it came back. Yeah, I can figure this out. Okay. X3 was -1. X1 was
1.
1.
X2 was 2.
Yeah.
Or -2.
Yeah.
It was positive 2.
X1 was 1. Do you remember?
X2
What?
was 2. And
Was
X3
2.
was negative.
Okay. This is interesting that I would have written exactly, almost exactly over. And what was my X2, that 2 was almost right on top of what was my 2 was there, and I would erase it all, but it's okay. I can write it back. Strange. Okay. So they wound up with the X vector is 1, 2, -1. And that's what they got in the book.
Okay, so
Okay.
you're looking by that because that's X1. That's X2.
Got it? Okay. And that does finish 2.4. So homework exercises here. Any of the odds 1 through 7, either 9 or 11 or both, either 13 or 15 or both, any of the odds 17 to 21, either 23 or 25 or both, any of the odds 27 to 33, And then a true-false number 35, probably won't see one like it on the test, but not a bad idea to think through that and know why it's true or false. Number 37 is a writing exercise. You can think through that again. I don't think you have to write down anything. 39 is a good one to do. 41 or 43 or both. 45 and 47. Now, here they go to doing this again, which I find at least irritating, but they define a new term in the exercises. Why wasn't this in the text somewhere if it was important? The trouble with this one, I don't even know how to pronounce it. Idempotent? To me, that word means nothing. Matrix. Determine whether a matrix is idempotent. Idempotent, I don't know how you say that. A square matrix A is
Equal to A.
Yeah, it's when A squared is equal to A.
So basically it has to be zeros and ones.
What's that?
It has to be just zeros and ones.
Yeah, well, yeah, you would, have to have that, but that doesn't guarantee it. So do 49 and 51 to determine whether or not they are idempotent, or however you say that. And then 53 is also that, determine the values A and B that make 53 idempotent, okay? Or however you say
Zeros.
it. Yeah, but which one? Okay.
Both of them. Well, let's see.
Yeah. If 49 is idempotent, then zeros will make 53 that. But you have to find that out one way or the other. Then there's some proofs and guided proofs, 55, 57, 59, if you're interested in doing those. And that's it. So let's move on to 2.5. So let me get, no. Here. All right, to erase. Now, applications of matrix operations. I'm pretty sure that I usually skip this section. Let me just see if New room. This class, though, about the same time, wasn't it? I don't know. If someone
The closer you are,
tainted my book, I don't know. I don't think I've done any of this section before. So let's just skip this one. Yeah. I'm so sorry.
So bad. Chapter 2.
What's that?
That's the end of chapter 2.
Yeah, so I should have had, well, in fact, I think I do have your test ready. I left it in the other room. I may have to make a copy, but I do have it ready. I left my tissue in the other room, too. This did happen to me on Friday, not to as big extent as it did last Thursday. But I was on the phone with someone and just got, well, actually, I called the person, and while the phone was ringing, it started. And I was starting to hang up, and she said hello right then. So I had to excuse me and just go back and forth. And we got the conversation in barely, and then my nose started bleeding. So I said, I'm going to have to hang up. My nose is bleeding. And she had heard it all. So anyway, all I want to say about 2.5 is, in case you need this, they have terminology here, stochastic matrix. And have you taken any chemistry?
High school.
Yeah. Did y'all use that word? Stoichiometry. Okay. It's the same type of a root here. You're making things basically balance, and But anyway, that's enough to say about that. Let me, we're not going to do anything here, so let's go over quickly what your, no homework here. Your test will be, I think, 2 questions from chapter 1. I can't remember which 2 sections they were. They're the ones we focused on. Oops. Chapter 2 still.
Gaussian elimination and Gauss-Jordan elimination.
Say that again.
Gaussian elimination.
Gaussian elimination, and then let's see, was the other one? But they're pretty straightforward. I think it was Gaussian or Gauss-Jordan elimination. And then, picking up here, the sections we did do 1 through 4. And so about two questions, approximately 2 questions on each section. Okay. So that's all we're going to do here now. I thought maybe that last section had something else in it, but it doesn't. Let's move on to start chapter 3, determinants. I think it sounded like you're already pretty familiar with these, or not?
Determinants?
Yeah. Thought so. So this probably will go pretty quickly.
Did you say you had the test for us, or
yeah, I may have to run it off. I have it made out, but I may have one copy. But you want me to go check now?
Yeah.
Okay. So why don't let me pause this again. Now, if you have a square matrix, well, 2 equations, 2 unknowns that you could use. A11x1 plus A12x2 equal to B1. A21x1 plus A22x2 equal B2. Now, if we were going to use elimination by addition to solve this matrix, several ways we could do. We could say multiply the top equation by negative A21, the bottom equation by A11, and add those together and solve for x1. Right. No, that would eliminate x1 and solve for x2. And continue like that. If you went through that, let me get my signs right. Yeah. Multiply this by a negative A21. Multiply this by A11. Okay. When you did that, your first terms would eliminate, and you would have A1, 2, A21 minus there, A11, A22 with a plus there, times x2 would be A11 B2 minus A21 B1, right? And x2 would equal A11 B2 minus A21 B1 divided by A11 A22 minus A12 A21. Okay? they wrote them in different form, but yeah, they got the same thing. I put the A's before B's, they put B's before A's. Okay. And similarly, if we had done for X1, then you would have multiplied this one by, let's see, get my sign right here. Let's see. Get my eraser in here, so this is hard to see. Okay. This time we're going to, okay. The eliminating x2, we'll either multiply by, and let's see, yeah, a minus a22 and minus a12. I think is how we did it. Okay. That would eliminate your x2s, right? Yeah. And that would give you let's do it the same way they do. B1 times A22 minus B2 times A12 divided by A11 A22 minus A12 A21, right? Now, something to note there. Your denominators are identical, right? Okay? And what those denominators are the cross product of your main diagonal minus the product of your other diagonal. That makes your denominators. And that's what we define to be the determinant of the matrix, of that original matrix. Now, what else did we do? In the x1, you always have, well, you do have another determinant, but what we've done here is rather than writing this coefficient, these coefficients, write this in its place. B1 times A22 minus B2 times A12. And that gives you your numerator here. And this one, you put the B1 and B2 in for these. And that would give you A11 times B2 minus A B2 times A21. I'm sorry, B2 times A B1 times A21. Okay, and that's exactly what you got for the second, which covers the whole section. I mean, that's exactly what we're doing with matrices. Okay, but before we went that far, they define what a determinant of a matrix is, which we just did. Oh, a 2 by 2 anyway. It's equal to, this is the matrix A11, A12, A21, A22. Then the determinant of this matrix, and they write it several ways. I really don't care for the DET, okay? It's certainly a legitimate way to write it. To me, it looks like absolute value bars. It's not, okay, because it's not always positive or anything. But this is the easiest thing to write, and that is equal to the product of the main diagonal for a 2 by 2, A11, A22, minus the product of the anti-diagonal, or the other diagonal, A12, A21. Okay? And again, they write the 2-1 first. It doesn't matter. Okay? positive this minus that. Okay? So, that's what a determinant is for a 2 by 2. We'll get into what to do from there on. So let's do example 1. Let's clear some space. This is pretty easy stuff, right?
Yeah.
Here is matrix A. 2, -3, 1, 2. What's the determinant of A?
That would be 4 plus 3, which is 7.
7. Perfect. Okay. B. 2, 1, 4, 2. What's the determinant of B?
4 plus 4, which is 8.
Eh.
4 minus 4, which is 0.
0. Very good. That's important. Okay. C. 0 to 3 halves. 2, 4. What's the determinant of C?
3.
Perfect. Oops, -3, isn't it?
Yes.
Okay. So, simple 2 by 2s, that's how you do it. Now, this next thing, the wording is a pain in the neck. The definitions and stuff. The doing it, if you don't let the wording confuse you, is pretty reasonable. Okay?
So is this the one where you pick the row and then it's plus minus plus? Minus,
Right,
plus,
exactly.
Minus,
Yeah. And
That's not too bad.
no,
You
it's
gotta
not.
actually do it, not
Right.
worry about the jargon as much.
Exactly, that's what I'm saying. The minors and cofactors and remembering what's what, and
Let's just skip that.
okay. All righty. Yeah. Well, then example 2.
Yeah, better to learn by example with this one.
Yeah. Now, number 1, let me say this while I'm still thinking of it. You can only take the determinant of a square matrix. And every square matrix is associated with that real number called the determinant. Okay. And whereas matrices can be big, long, hairy things, its determinant is a single number. A single number. Okay. It's kind of like vectors and scalars. You know, scalar is just a number, a vector is a lot else. Okay. I think I'll clear the page. And you're all in favor of not messing with the nomenclature? Okay. I'm afraid you might need it sometime, but you can go back and learn it if you do. Let's just do, here's a matrix A. And it's 0, 2, 1, 3, minus 1, 2, and 4, 0, 1. Okay. Now, one of the first things you do here is for the 1, 1 entry, which happens to be a 0 here, its minor would be eliminate the first row, first column, take the determinant of what's left. And what do you have?
That would be -1 minus 0, which is
-1, exactly. Now, why split these up into things when it just makes it so confusing? What makes that's the minor. The cofactor is then whether that's a plus or a minus. Okay, obvious -1 is a minus, but why is it? Well, this is a plus position here. Okay, because the diagonals are always plus, your corners are always, your upper left and lower right corners are always plus, and that's where you start counting from. So the cofactor is also -1. Okay. Now,
So if it was a negative, it would have been +1 because it flips the sign, right?
yeah, okay. That was the cofactor for 1, 1, and the minor for 1, 1, and then the cofactor is the same on 1, 1. Okay. Now, pick another one. I don't care. Pick one. Name it by its location.
2, 2, or 2. Well, it would be 1, 2.
1, 2.
So 2.
First row, yeah, this 2 right here. Okay, what you do to get the minor, you cross out the first row, second column. Okay,
So
and
3, 1, which is 3, -8, which is -5.
okay, so that would be -5. Okay,
The factor for that will be negative, so it's a +5.
+5, you got it. Okay, so that's all they're doing on this. Okay, and it's just keeping straight what's the thing. Now, easier than that is just, okay, now how they suggest that you, not just suggest, say that you determine, you look at those subscripts. 1, 1, 1 plus 1 is 2, -1 raised to the, an even power is positive. 1, 2, 1 plus 2 is 3, raised -1 to an odd power is negative. So, do I ever do that? No. I just do plus, minus, plus, minus, plus, minus, plus, minus, you know.
Well, I mean, if you look at it, all you got to tell us that if the position adds to be an odd number, then it's going to be negative. If it has to be even, it's going to be
right.
the same.
That's exactly what they're doing.
But you don't have to think about putting it up to. I mean,
Exactly.
It makes sense, but that seems extraneous.
Yeah, but that's how you have to,
Justify it.
well, program a computer to get it to do it, because it can't say, is it even or odd, you know. It does it that way. Same thing. So that's how they do it. All right. So I think we've figured out what these are and why waste the time of doing them all. Okay? Did I say that out loud? Okay. The definition below is inductive because you have to induce your answer out, which is a rather long process. So I'm going to erase all this and proceed from here. If A is a square matrix of order n greater than or equal to 2, so A square order greater than or equal to 2. Well, guess what? All it's leaving out is a 1 by 1, which is not very interesting at all, a single number. So I don't know why they go to all that, but anyway. Then the determinant of A is the sum of the entries in the first row of A multiplied by their respective cofactors. Okay? That is, and here's how they write it, the determinant of A is the summation J equal 1 to n, and this is an n by n matrix. Okay, so that's where the n came from. J is just a counter. And you can do A1J, C1J, okay, which would be A11, C11 plus A12, C12 plus A, and dot, dot, dot until you get A1N, C1N. Okay. That's the determinant of A.
Okay.
Or you could choose any row. Or you could choose any column. You know, you just have to change it around a little bit. I1 or I7 or whatever it is up to n, and just do them all that way. It doesn't have to be the first row. It can be any row, any column. And that's really nice and important for you. Okay? So when you use the definition, you have to evaluate a determinant. You're expanding the cofactors in the first row, which is fine. So let's actually do one, but do it more reasonably. Yeah.
Sorry.
Am I skipping too much?
No. I was gonna ask. Right. So the determinant of a 3 by 3.
Uh-huh.
It's gonna be a number.
Right.
But you have to take the determinant of each little block.
No. There is a shortcut for a 3 by 3.
Okay. But
Yeah.
if it was like a 7 by 7.
Yeah. Anything bigger than 3 by 3, you got it.
You gotta like start with 1 by 1 and then,
Well,
that would be different.
no, it's, we'll get to it.
Okay.
Let's first do it their way on a 3 by 3, and then I'll show you the other. Here's A. It's the same one I think we had before. 0, 2, 1, but we didn't do them all, so that's okay. 3, -1, 2, and 4, 0, 1. Okay. Now we're going to do it the first row just like they suggest, and that's the best way to do this one. Okay? So what you do is this number here, 0, times its determinant. Not much to do there. Okay.
I can do that.
Yes, thank you. And actually, even better than that, you have to have the sign of it, which is positive 0 times its determinant. So, yeah. So that one's done. So let's go on.
-0.
Yeah, that gives you problems, doesn't it? Okay. All right. Then this one would be a -2
Okay.
times its determinant of the cofactor.
Which would be 3 minus 8, which is -5.
Okay. Okay. So I was starting to write the determinant of the thing, but since we're doing that, you've already determined it. I don't want to put those bars because that makes it look like absolute value. Okay. And then we do the 1, and that's a +1 times its determinant, which is
3 minus 8, which is -5 again.
it's what?
-5.
How do you get that?
3 minus 8.
How do you get that?
Oh. 0
Uh-huh.
plus 4.
All right, good. So this will be
I mixed that all up. Okay.
10 plus 4 is 14.
So that's the determinant of this matrix.
Mm-hmm. Exactly.
You just have to do it for one row
That's it.
or one column.
Or one column. So let's do it for, say, the first column.
I would say let's do it for either the first column or row 3. Okay.
Or what?
Or row 3.
Or row 3 or column 2. Okay. You got the idea, yeah, extraordinarily. Okay. So let's do first column. That's a positive, but it's a 0, so forget that. The 3 is a negative position, so -3 times.
That would be 2 minus 0, which is 2.
Okay.
Alright, and then we get 4 place, and that's a positive 4.
Right.
Times 4 minus -1, which is 5. So 20 minus 6, or -6 plus 20, is 14.
Again, it didn't matter, did it? Okay. Do you want to do one of the other two? You take my word for it. Really trusting soul you are. Okay. So pick a row, pick a column, any row, any column, and do the determinant. Now, 3 by 3.
Zeros are your friends.
Definitely. Now, since we're there, let me show you the easy way.
That wasn't the easy way.
That was pretty easy.
That was
But
easy. You
any-
don't have zeros in it.
Any 3 by 3, you can also do this. And this may actually be a little harder on this one because that was so easy, but this will work on any one. Okay?
You want to make a new matrix for it?
No, we'll want to make sure that we aren't making something up. Okay? So what I'm going to do is repeat the first two columns. 0, 3, 4, and 2, 1, 0. Now, this isn't quite going to be the same, but it's pretty close. I want to close that off, but if I do, you'll think that's not a square matrix. Whatever it takes. Do a dotted line there, something. Okay? Do your upper left to lower right diagonals and get what you got. What's that? 0. Yeah, 0. This one? No, you're multiplying.
2 times 2 is 4. 4 is 16.
16. And one more?
0.
0. Okay? Then do your minus. Now, you got to have 3s, so minus this one.
That one would be 4.
Plus 4. Okay? That one, a 0. And that one's?
Is that a negative? No, it's not. That'd be 6.
Yeah, minus 6. But it's a minus because you're going upper left. And what does that add to?
14.
14. So that's the other way. It's a little more writing up front, but a lot less calculating otherwise. And your zeros are still your friends. Huh?
I feel like it's really close to the same thing, but I mean...
It is. It's exactly the same thing.
As we go along it.
But it won't expand to 4x4 or anything else.
Yeah.
That only works here. The 2x2 works, has a real special feature too. It's so easy. But there's also something else, and we'll get to that as well. Okay. Now, and by the way, at the bottom of the page there's a thing saying, try other possibilities to confirm the determinant of A can be evaluated by expanding any row or column. We did that. The following theorem states this is known as Laplace's expansion of a determinant after the French mathematician Pierre-Simon de Laplace. Okay? So there's a couple of potential paper topics there, right?
We've been out of time for like 5 minutes.
Okay, sorry about that.
No, it's okay.
We will start next time. I didn't bring a pencil in. Do you have a pencil with you? Pencil?
Yeah.
Okay.
That's okay.
We'll start with
It's just fancy.
3. Theorem 3.1.
But
Let's see,
it's
did we get enough
it's
done
like
to
12,
do?
21.
Yeah. I think you can do any of the odds 1 through 11. 11 is sort of interesting. Try it. 13 or 15, that's minors and cofactors. 17 if you'd like. Any of the odds 19 to 25, actually 19 to 31. And guess what? You don't have to do by expansion by cofactors. Do it however you like. And then 33. And if you want to try it, 35, big decimal numbers. 37 is pretty easy. And we'll stop there. And pick up and go. I want to make sure I only turn this off.
Don't forget to stop screen.
Yeah. I'll stop this.